Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we will be learning about trapezoids. To get started, let's look at the following problem. In a quadrilateral ABCD, measure of angle A equals to measure of angle B, measure of angle A is equal to x plus 25, measure of angle B is equal to 2x minus 40, and measure of angle D is equal to x minus 12. Compute the measures of each of the angles of this quadrilateral. So, how do we solve this problem? Well, let's first draw a quadrilateral and label the angles, and then we proceed from there. Okay, so here's the quadrilateral with all the angles that are labeled. Obviously, this quadrilateral is not drawn to scale, specifically due to the fact that measure of angle A and B are equal. Okay, so there's already something we can do here, right? We know that measure of angle A equals to measure of angle B, which is given. And all we need to do here is just substitute with x plus 25 for measure of angle A and 2x minus 40 for measure of angle B, and then just simply solve for x. And once we solve for x, we obtain an x value of 65 degrees. Okay, so at this point, let's back substitute to find each respective angle measure. So once we substitute, we obtain an angle measure for A to be equal to 90. Measure of angle B is equal to 90 as well. Measure of angle C, we don't know yet, but we know that the measure of angle D is 53 degrees. So how do we find the measure of angle C? Well, we know that in every quadrilateral, the sum of all measures has to be equal to 360. Obviously, here we're talking about the interior angle measures. So that means that if we sum it all up, and let's say we call the measure of angle C equal to x, summing it all up, we obtain 233 plus x. That must be equal to 360 degrees. So that gives us an x value of 127. And by the way, a little side note here. Here we picked the value of x, which is different than the value of x in the previous problem where we figure out the x value. So we know that now the measure of angle C must be equal to 127 degrees. Okay, so that's basically the answer here. Now let's draw it a little more to scale. So we know that the measure of angle A and B are both 90 degrees, okay? So let's draw that in. Okay, so this is now the image that is drawn to scale. As you can see, we have angle A and B both perpendicular, and then we have angle C to be 127 degrees and angle D to be 53 degrees. So what kind of shape is this? Okay, so before we get into that, let's look at the fact that segment BC is perpendicular to segment AB, and also segment AD is perpendicular to segment AB. So, and we know from the theorem that if two segments or two lines are both perpendicular to the same line, then these two segments, they must be parallel, okay? So now we have a pair of sides that are opposite and parallel, but not the other two. And what kind of shape is this? Well, it turns out that this is going to be a trapezoid. And this is the introduction to today's lesson on trapezoids. So as we did in previous lessons, regarding all the other quadrilaterals, let's first introduce the definition of a trapezoid, and then we'll introduce the properties as well, okay? So the definition of a trapezoid states the following. A quadrilateral is a trapezoid if and only if it has at least one pair of parallel opposite sides. That's an interesting definition, right? Because it states that there's at least one pair of parallel opposite sides. So that means that the bases that are parallel and shown here in the diagram are not necessarily just the only parallel sides. Also the legs that are not necessarily parallel could actually be parallel as well. So what does that mean? It means that every parallelogram is considered a trapezoid. So let's go back to the hierarchy of all the quadrilaterals that we did in the previous lessons. So here's the hierarchy of all the quadrilaterals that we have learned so far. As you can see, we learned first parallelograms after we introduced the concept of quadrilaterals. But it turns out that a parallelogram is indeed a trapezoid because of its definition of having at least one pair of parallel opposite sides. So if we look at the regular trapezoid here, so from the definition, we can see that there are really no properties for the trapezoid itself, okay? Okay, so now that we know that trapezoids have no properties, we have another subcategory here, which are isosceles trapezoids, okay? So let's define that one and see what the properties are. So here's the definition of an isosceles trapezoid. A trapezoid is an isosceles trapezoid if and only if the base angles are congruent. So basically, if we look at the image here, we can state that these angles here, so let me draw that in really quick, maybe use a different color. So these angles here are considered the base angles, okay? And they must be congruent to be an isosceles trapezoid. Alternatively, you can also state that these two segments or these two legs must be congruent as well. So if the definition states that a trapezoid has at least one pair of opposite parallel sides, then what other shape could this be such that it's still considered an isosceles trapezoid? Yeah, that's right, a rectangle. So if we look at this rectangle here, why can we say that this is also considered an isosceles trapezoid? Well, because the opposite sides are parallel, okay? We have at least one, and we have the base angles that are congruent right here, right? These are the base angles. So it doesn't matter if these segments are parallel as well. That doesn't matter because it still satisfies the definition that at least one pair of opposite sides is parallel, okay? So, and that is the reason why, if we go back to the hierarchy here of all the quadrilaterals, that is the reason why isosceles trapezoids here are connected with rectangles, because every rectangle is also considered an isosceles trapezoid, okay? So now that we have the hierarchy here, we can also think about what the properties are of an isosceles trapezoid. So let's go back to discuss the properties here, okay? So what are the properties of an isosceles trapezoid? Okay, so the first property of an isosceles trapezoid is that the legs are congruent. But again, if it's a rectangle, then the legs could be any of the opposite sides, okay? What else must be true in terms of properties for trapezoids or for isosceles trapezoids? Well, a second property is that the base angles must be congruent. Okay, so another property has to do with diagonals. So let's draw them in really quick. So let's say we have these diagonals. What must be true about the diagonals? The diagonals are congruent. Then there's one more property here. And this property has to do with angles, okay? For example, let's refer to angle A and C, okay? And similarly to angle B and D. Okay, so what must be true about these opposite angles? Well, if we think about this, right, if angle A and D are congruent, then angle B and C must also be congruent, right? Because this is an isosceles trapezoid and it can be easily proven. So it turns out that opposite angles must be supplementary. So this is basically it with all the definitions of the trapezoids and the isosceles trapezoid and the properties of an isosceles trapezoid. Now, as we did in the previous lessons, we actually want to prove these properties as well, so we can claim that these properties are always true. We don't really need to prove the first two, that the legs are congruent and the base angles are congruent, because these are really part of the definition. However, we can definitely prove that the diagonals are congruent and also the opposite angles are supplementary, okay? So let's prove the fact that the diagonals are congruent first. So according to the figure here, we're given that ABCD is an isosceles trapezoid, and we're also given that segment AB is not parallel to segment CD. Here we're given this because if, let's say, we weren't given that segment AB and CD are not parallel, then we can simply state, oh, it's a rectangle, and in a rectangle the diagonals are congruent. We already proved it. So that's why we're going to state that these two legs are not parallel, so we can deal with this special case of isosceles trapezoids. So again, how do we prove that segment BD and CA are congruent? So let's get started with setting up a statement reason table. So here's the statement reason table. And as a first given, we want to state that ABCD is an isosceles trapezoid. Well, at this point, we can use the definition, right, of the trapezoid. That's really the only thing we can use here because we don't want to use the properties because that's what we're trying to prove here. Now, when we consider the definition of an isosceles trapezoid, all we know is that the base angles, as shown in the figure, are congruent. So let's write that in the statement reason table. Okay, so once we write that in, what else can we state here? Well, let's think about this. What we can do here is prove triangle BAD congruent to triangle CDA. And that can be easily done because we have a pair of angles. We also know that segment AD is congruent to itself. And then we need another set of either angles or segments to prove it using either the SAS or the ASA postulate. But let's look at this first. So let's write that segment AD is congruent to itself. Okay, so what else do we know about isosceles trapezoids? Well, we know that these segments here, which are the legs, must be congruent as well. So let's write that in. So basically, segment AB is congruent to segment CD because the legs of an isosceles trapezoid are congruent. And now we have all the ingredients to prove the triangle's congruent. Therefore, triangle BAD is congruent to triangle CDA because of the SAS postulate. And then finally, segment BD is congruent to segment CA, which are basically the diagonals here, because corresponding parts of congruent triangles are congruent. So now we know for sure that the diagonals of an isosceles trapezoid are congruent. So that is now a property that we can always use here. So the other property that was mentioned before earlier during this video is that opposite angles are supplementary. So how can we prove that? That's actually a very simple proof to do because what do we know here about the definition of an isosceles trapezoid? Well, in this case, we know that these two opposite sides are parallel, correct? So since they're parallel, we can say that angle BAD and angle ABC are supplementary. Remember why they're supplementary? Well, the reason is if two parallel lines are cut by transversal, then same side interior angles are supplementary. Again, we know that they're parallel lines because that's just the definition of the isosceles trapezoid. Similarly, we can say that these two angles are supplementary. Similarly, we also know that angle CDA and angle BCD are supplementary because of the same exact reason, right? Because if two parallel lines are cut by transversal, then same side interior angles are supplementary. Now, here's the thing. We know from the definition that these two angles here are congruent. So we're basically saying that angle BAD, this angle that I'm highlighting here, and angle CDA, they're both congruent, okay? So let me denote that in the diagram that this is congruent, okay? So that means that if they're congruent, we can actually swap them, or we can substitute it and write the following here. That angle BAD and angle BCD are supplementary. Notice that we're saying that these two here have to be supplementary as well, again, by the substitution postulate. So that basically proves the point that the opposite angles here, so if we draw this in here, that these are the opposite angles, they must be supplementary, which is part of one of the properties that we developed before, right? Well, similarly, we know that these could be swapped as well. That angle CDA and angle ABC are supplementary. So these are the other pairs of opposite angles, and they also must be supplementary. And that's a fairly easy proof. Therefore, we can state with certainty that opposite angles of an isosceles trapezoid are supplementary. Okay, so that's basically it for this proof. Let's quickly summarize what we have learned in today's lesson. So again, in today's lesson, we learned about the definition of a trapezoid, where the most important part here is that we have at least one pair of parallel opposite sides. We also learned that trapezoids do not have any properties. Then we learned about isosceles trapezoid, so we learned about the definition, and as a matter of fact, the isosceles trapezoid can be defined in terms of base angles that are congruent or in terms of the legs that are either parallel or non-parallel that are congruent. We also learned a few properties here, that the diagonals are congruent and opposite angles are supplementary. We also proved it. And finally, we looked at the hierarchy of all the quadrilaterals that we have learned so far. And we can see that parallelograms are part of trapezoids, which are part of quadrilaterals. And the isosceles trapezoid is a subcategory of a trapezoid. And rectangles are basically a subcategory of isosceles trapezoids, but also parallelograms. And that's basically it for today's lesson. I hope you enjoyed today's lesson. Again, thank you for watching and have a wonderful day.